Fine. Fine. Oh, doesn't sound too good. Must be a blockage here. Something else to fix. First, another scientific investigation. What are you up to up there?
Stella, we've been experimenting. Watch. When I tap this glass, the wire on the other glass wobbles off.
It's to do with vibrations, isn't it? Tapping it makes the glass vibrate, and the vibrations travelling through the glasses, making the wire wobble.
Yeah, but the glasses aren't touching, are they? So how can one glass make the other glass vibrate?
And watch this. When I take an even bigger glass and tap it, the wire doesn't wobble off at all.
Well, maybe the bigger glass isn't vibrating enough.
Stella, can you investigate?
Okay. Sound, vibrations, wobbling wires. What's the connection? Well, think of all the ways sound is made. We can make it ourselves. Machinery can make it. Natural sounds like thunder, wind, waves. But probably the single sound you hear the most is the sound of your own voice. But all these different ways of making sound have one thing in common. They're produced by vibrations, and you can feel these when you put your finger against your throat. As I pull the bow across the string, the bow makes the string vibrate backwards and forwards very quickly. By using a strobe light, we can see the individual vibrations more clearly. All musical instruments need something to vibrate to make the sound. This loud sound is caused by my lips vibrating. This is a more unusual way to cause vibrations. Rubbing my hands on the handles causes the bowl to vibrate, and it makes a sound. But look what's happening inside. But is it the sound causing this? I need more evidence.
I'm off to the Institute of Sound and Vibration Research in Southampton to find out just how powerful sound can be. I'm meeting Professor Fahy, who's experimenting with some pieces of paper. Wow! Was that the sound that was causing the paper to move like that?
Yes, it was, but I had to make a very loud sound to make it happen.
But what actually makes sounds loud?
Well, you know that sound is caused by things that vibrate, and the bigger the vibration, the louder the sound.
When I hit this drum gently, the vibration is very small. The polystyrene balls only just move, and the sound is quiet. The loudness of a sound depends on the size of the vibrations that made it. The size of a vibration is called its amplitude. The bigger the amplitude, the louder the sound. So sound can move pieces of paper, but let's put sound to the test and see what it can do to this. I've built my tower on a toughened glass sheet, and underneath is a speaker through which the professor is playing a sound. Able to knock down my tower without using the big, powerful vibrations of a large amplitude sound?
Well, Femi, that's because there's something else involved, and that something is called frequency.
When you tap this glass, it makes a sound as it vibrates. This piece of equipment counts how many times a second the glass is vibrating. The rate at which something vibrates is called its frequency. Frequency is measured in hertz. This glass is vibrating 400 times a second, so the sound has a frequency of 400 hertz. This sound has a frequency of 200 Hertz, and at that frequency the sound makes the sheet of glass vibrate so much that the tower topples.
Okay, so sound can move paper and it can cause enough vibration to make a tower topple, but what could it do to a wine glass? Could we break it?
Well, I don't think so. We've never managed to do it before. But if we use the right combination of frequency and amplitude, we might see something interesting.
So if we used a sound that's a very large sound with a very large amplitude and a frequency, that's the same as the glass.
That's right. Let's experiment.
This experiment's conducted in a specially soundproof room to stop us being deafened by the very loud sound we're going to use, which is louder than Concorde at takeoff. A strobe light helps us see more clearly what's happening. And look. The sound is making the stiff glass behave like jelly.
Impressive stuff, Femi. But I've got my own frequency generator here. Now, when I shorten the length of the overhanging ruler, the frequency of vibrations increases, and you can hear the sound change. It goes up in pitch. Listen. So higher frequency means a higher pitch. Lower frequency, a lower pitch. Higher amplitude, a louder sound. Lower amplitude, a quieter sound. Frequency and amplitude are totally different, but sometimes it's hard to tell which is which. What's changing here? Frequency or amplitude?
Frequency or amplitude.
So there's definitely amplitude changing there.
I've got another amplitude puzzle here. Listen. Quiet, isn't it? But listen what happens when I put it onto this table.
It gets louder. Why is it louder?
We must be making bigger vibrations somehow. You're turning it exactly the same, so it can't be making bigger vibrations.
Stella, we need your help. What's happening? What's making this sound louder?
My fellow musician Liam can help explain. Even in this bell jar, you can still hear him playing. But listen to this. As I remove the air from the bell jar, he gets quieter. Why? Imagine you could see what's happening to the air as I hit the skin of the drum. The air is made up of many tiny particles that surround the drum skin. When I hit the drum, the air particles next to the drum skin vibrate and collide with each other. In slow motion, you can see the vibration pass along the line of air particles. It's called a compression wave, because the particles are compressed together. The vibrating particles pass the sound through the air into your ear. So the less air in the bell jar, the harder it is for the sound to be heard, until with no air at all, you can't hear a thing. Sorry, mate. So sound needs particles to transmit the vibrations, but they don't have to be air particles.
Where's that noise coming from? How can I concentrate with all that?
There's someone out here who knows a lot about sound. Dr. Vasu Devan. Maybe she can help.
Right, that's fine, let's take a break.
That was very beautiful, but it doesn't exactly help me concentrate.
I'm trying to find out what medium sound travels through, but all I can hear is their music.
You were sitting in a concrete room with a closed solid wooden door.
That's right, and I can hear myself think.
Well, there. 2 more materials the sound can travel through.
Wood and solid concrete. I never thought about that. How does sound do that? Travel through a solid concrete wall?
Let me show you something.
A music box?
Go to that corner of the hall. You'll find some equipment I've left over there for an experiment.
There's no scientific equipment over here, just a tin and string.
That's it. Can you hear the music box?
No chance.
Okay. Now put the tin to your ear.
No problem. Just like a string telephone.
Exactly the same. You see, not only does sound travel through solids, it actually travels through some solid objects better than it does through air.
Each of these dancers represents a particle of a solid. They could be string particles or concrete particles. Because they are a solid, these particles are in fixed positions and are very close together. So when one particle vibrates, it makes the particle next to it vibrate, and so on. So the sound travels very well through the material. Why did we need a tin at the end of the string?
The vibrations passing along the string were still very small, very low amplitude. Not enough to cause sufficient vibrations in the air for the sound to reach your ears.
But when they reach the tin, so pop it on there, they caused the surface of the tin to vibrate, and the larger surface area of the tin meant that larger vibrations of the air reached my ear.
That's right. It's called an amplifier because it's amplified the sound.
What are the girls actually doing?
They're synchronized swimmers rehearsing for an underwater routine.
Underwater? They're going to have a bit of a problem hearing the music underwater, aren't they?
Do you think so? Think of particles in a liquid.
This time the girls represent particles of water. These particles are not in a fixed position, but they're still close together, and a vibration or sound wave is still able to pass from one particle to the next.
So sound should have no problem travelling through water. Let's see. I have a specially designed microphone that can go safely underwater. It's wired up to a speaker so we can hear what the microphone's picking up. Okay, Latta?
Above the water, I can't hear the submarine's motors at all. But underwater, what happens? Will the microphone be able to pick up the sound? No problem.
So with their waterproof speaker, the girls don't have any problem hearing their music after all.
So sound can travel through solids and liquids as the particles vibrate. But what happens when a sound wave meets a material like this, a hard, flat surface? Some of the sound is reflected off the surface. This sound reflection is called an echo. At sea, echoes are very useful. When sailors were stuck in fog, they'd blow their foghorn and listen to see if the sound was reflected back from the cliffs. But if there was no echo, then they were safe. Nowadays, ships and submarines use echoes in a more sophisticated way to locate rocks or shoals of fish or the sea bottom. Sonar transmits sound waves into the sea. The sound is reflected off any object it meets. The sooner the echo returns, the nearer the object.
To find out more about what happens to sound when it meets surfaces, I've come to Scotland, to the Hamilton Mausoleum. Apparently, this building has a very strange effect on sound.
Sounds okay to me.
Hi,
It's the reverberation time.
What?
It has the longest reverberation time in Britain.
What's going on in here? This is crazy.
Sound is reflecting off all these hard walls and getting very confused in here. Let's go outside. Now, out here, the sound can travel in all directions and none of it is reflected back to cause any problems. Inside, the sound was being reflected from all the hard surfaces and causing a confusion of sound inside the building. Each individual reflection is an echo and all the reflections together are a reverberation.
An oscilloscope helps us measure just how long the reverberation lasts. It detects the sound as it's reflected off the walls.
Ready, Les? 3, 2, 1.
You can see how the trace gets smaller as the sound fades away until you can no longer hear it.
And the reverberation lasted 15 seconds. La 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 la.
When the sound waves hit the hard, smooth walls, most of the sound reflects back into the room. So I still hear the first note whilst I'm singing the second, and so on. But most rooms aren't like this. They have a lot of soft, absorbent materials like carpet or curtains.
Les, if we got some material which can absorb sound and put it in here, would it make much of a difference?
Of course it would, and I have some material that will do that very job. You can see it's very soft. It's made up of fibres, and these fibres, when the sound comes onto the material, move, and they will absorb the sound.
La 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 la. Now when the sound waves hit the soft panels, most of their energy is absorbed and very little sound is reflected.
So, now for the test. 3, 2, 1.
This time, much less sound is reflected off the panels. It fades quickly, as the shorter trace shows.
6 seconds. So the panels have made a huge difference.
Sound a lot better if it was in tune. But how can just tightening a string change the sound?
It changes the tension in the string, doesn't it?
Yeah, tightening the string is going to stop it vibrating, isn't it? No, tightening the string means it'll vibrate faster, even more frequently.